Top lecture. So today and the next Monday, we are going to be talking about statistical methods. And the statistical methods, in some sense, is the other side of Monte Carlo methods we looked at a little bit before. So Monte Carlo method is saying that we already know the distribution of some uncertain factors. And we want to analyze the effect of these uncertain factors. But you might be wondering, how do we know the source of these uncertainties anyway, right? Usually, we can observe some uncertainty from certain data, right? So data basically tells you, even under identical conditions, everything you can control, the outcome of something might be different from one time to another. So that is a good indication of there is something you either don't have control or don't understand yet, right? So like the weather or the wind we have looked at last time is something maybe we have some understanding, but we don't have control, right? That's actually an extreme situation where we have a environmental factor that is completely out of our control. The more often situation is that we have some environmental factor that is partially under our control. So what that means is that if you collect data on the outcome and some variable we think we can control, we find that the outcome and control doesn't follow a perfect relation. So there is some scattering in the data in some sense. And statistical modeling is basically trying to figure out what that relation is, and also try to model what is the residual, what is the additional noise on top of that deterministic relation you try to infer. And these are going to feed into your Monte Carlo simulation, right? So let's say I have an example of. So can somebody think of a good example of situations like that in engineering? I have my x-axis being something I can control, my y-axis being the outcome of the control. They are not completely decoupled, but they are also not deterministic function of each other. Yes?
Fuel flow rate and thrust.
Fuel flow rate and thrust. That's actually a pretty good example. In the sense that there is in the engine, there is actually a lot of things like that. So in the engine world, the most prominent example where something you can control but the outcome is very random is actually emission. Okay, so the axis may be a lot of things. For example, your fuel flow, or your thrust setting, or like actually you can in that scenario, the data I've seen is you have multiple x-axes. So you have your thrust, you have air density, temperature, a lot of other things. But even taken into consideration of all these factors, your emission, is there 2 M's or 1 M? Your emission actually has a lot of scatter. So basically, under the same conditions, if you measure two engines that are made from the same model, if you measure two engines that is supposedly the same model, you get quite different emission levels. So that's one of the things. For example, you get a data that is something like that, right? So this is the kind of things. So when you, for example, if you want to design the flight path of an airplane to try to both save fuel and cut down emission, then you have to consider this relationship, right? And up to now, it is still very difficult to simulate actually the actual emission of a jet engine combustor. It's very sensitive to a lot of things, the combustion, the geometry, and if you make a small variation in the geometry you simulate, they end up the emission can be quite different. I mean, that's actually why there is such a scattering. So we still don't really understand how do we control the geometry, the design of the jet engine to basically narrow down this gap, make it more stable. Okay, so that's the kind of things you may want to infer. And for this to be useful, you want to really model the trend as well as you can. For example, you want to have a blue curve, and you also want to have a model of at a certain fuel flow rate, what is the scattering, the distribution. Usually you can write it, you can represent it in such a way, right? So although if I look at that specific x-axis, I actually almost surely I have zero data on that specific fuel flow rate, right?
What are you exactly presenting?
So this is the conditional distribution of emission, given that my fuel flow rate is exactly at that vertical dashed line location. So effectively here I have zero data, right? At most I probably have one data if this is actually taken sample from real life as opposed to from a well-controlled experiment. So at some fuel flow rate I have one data point, at other flow rates I have no data point. But I need to come up with a model in order for me to design my flight path, for example. I need a model for what is the conditional distribution of emission at every single fuel flow rate. So there are actually a lot of examples like this in engineering. You need to look at the data, stare at it, and figure out a model out of the data that can both provide an explanation of some sort, that how does the emission depend on the fuel flow rate, and also have a model of the unexplainable part. All right, so that's what we are what we are studying here. And another aspect or another application of this that is popularized recently by this whole deep learning thing is there are a lot of scenarios where you can actually explain outcome that is not that is a function of not just the one variable like here, not several variables, but extremely large number of variables. A good example is image recognition. So in image recognition, the outcome of if the image is an airplane or a human doesn't depend on a few variables. It actually depends on the color at every pixel of your image. Right? Every pixel, red, blue, green, is 3 variables. If you have an image of 1 million pixels, you have 3 million variables to look at. So traditionally, there is no real good ways to perform statistical learning with your control variables being like 3 million. So the recent development in deep neural network really starts to make that now possible. The principle is the same, except for rather than having one horizontal axis, you have a huge number of horizontal axes. But the result is the same. You want to get a maybe 3 million dimensional surface or hypersurface that, given a point in this 3 million dimensional space, you want to estimate your emission or whether the picture is an airplane or human. And you also want to quantify how much uncertainty do you have on that answer. So that's basically what statistical learning is about.